Okay, next we're computing the new mean and the new standard deviation given that 4 months have passed. Now, very intuitively, if you think about it, you have two groups. Now, let's say we have one group of people, all of us here, and we're going to calculate your average age. And it's, well, in this case, let's say it's 25 years. Or no, here it was 30 years. Yeah, let's say your average age is 30 years. Now, 4 months go by. How's your average age going to change? Well, it's just going to increase by 4 months, right? Because it's the same people, everybody's getting older. So that was really easy. We just add the 4 months to it. That was all there was. And the standard deviation, how is it going to change if we get 4 months older, all of us? Well, it's not going to change because all the people are the same. Everybody increases by the same amount of age in years. So it's not going to change, and therefore it's the same. So 12 times 3, 36 months. Yeah, you only have to convert it into months here. So that's the only difference. Yeah, now moving on to binomial distributions. Very characteristic about binomial distributions, we have a probability of success and failure, and we have a sample size. Yeah, in this case, both is given. We have p, which is 4%, and the sample size is 30. And based on that, we want to find out the expected value and the expected variance. This is also really straightforward. Just look it up in the formula sheet. Under binomial distribution, you will find the expected value defined as n times p. So the sample size times the probability of success, in this case 1.2. And the variance is defined as n times p times 1 minus p. Yeah? So just formulas. Just know that you are applying the binomial formula here and not the other formulas because of the characteristics that you can see, which is why it's a binomial distribution. Yeah, that's always important. When you read the prompt, you can already tell it's binomial because you have probability and a sample size. And what's the big difference between binomial and Poisson? Anyone? What is the characteristic about a Poisson distribution? Anyone? Huh? It's the mu, yeah? It's the mu that we're actually looking at specific rates. With Poisson distributions, it's always about rates. So 2 cars per hour, 10 people per hour, and so on. So we're looking at times, right? With binomial ones, we're not looking at times. We're looking at a sample drawn, and we're looking at success and failure. This is how you differentiate. Okay, now we want to find the probability that at most one teenager has a tattoo. As you might remember, I said there are 2 ways to find probabilities. You either look it up in the table or you calculate it with a formula. If you do it with a formula, you always use it for x being equal to exactly one value. Yeah? If you look it up in the table, it's always x being smaller than or equal to a value. So there's the difference with the equality sign. In this case, if we want to do it with the formula, we have to set it equal to an exact value. In this case, 0 and 1. Yeah, because we have 2 cases where it's smaller than or equal to 1. If you were to look it up in the table, we would just take smaller than or equal to 1, just 1 as our k. Okay, now it's just simple plugging into the formula. And, hold on, where's this little... I'm looking for this thing where you can draw on, but it's not on here. Okay, but, well, never mind. But this, the 30 over 0 in brackets, yeah, just for repetition, it's the same as the factorial. So 30 and an exclamation mark divided by the factorial of 0 times 30 minus 0 factorial. Yeah, that's the same way of writing down 30 over 0 in brackets. And that eventually will be factorial of 30 divided by factorial of 30. So what is that? The factorial of 30 divided by the factorial of 30. Yeah? Yeah, it's just equal to 1, right? Because factorial means factorial of 5, for example, would be 1 times 2 times 3 times 4 times 5. That's what factorial means. So you can cancel out all the numbers. Therefore, our 30 over 0 in brackets, that's 1. 0.04 to the power of 0, that's also 1, because any number to the power of 0 is 1. So we eventually only end up with the 0.0 6 to the power of 30 as our first term. And the second term, well, the 30 over 1 in brackets, it already gives it away here, it's 30, yeah? How do we know it's 30? Because we have a factorial of 30 over a factorial of 29. So you can see, you can cancel out all the values from 1 till 29, except for the 30 that you have in the nominator. So, hold on. Factorial of 30 divided by factorial of 29. Yeah, so you can calculate all the values except for the 30 on top. It's like 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 2 times 1, right? This is the factorial of 4, this is the factorial of 5. We can cancel it all out. We will just end up with the 5 in case we have factorial 5 divided by the factorial of 4. So here we end up with 30, yeah? So that's why we have 40 there, and yeah, if you put it in your normal calculator like this, then you'll get a value of 66%. So the statement is true. Next, we're using the Poisson approximation to calculate the same thing. Yeah, this is one of the characteristics. We can also calculate it with the Poisson formula, namely a binomial distribution, in two situations. When the sample size is huge, so when the sample size is bigger than 20, for example, because then we don't have a table where we can look it up, right? We have our table based on the sample sizes, and if it's a really, really large sample size, we can't look it up in the table. And the other situation is when the probability is smaller than 5%. In this case, both is true. So we can approximate with Poisson, and the only thing we need to know with Poisson is the mu, right? So the mu is n times p, it's also in the formula sheet, that's 1.2. And with that information we can just plug it into the formula, so we have our x is equal to 1, we have our mu, and we plug it in and we will see it's not equal to e to the power of negative 1.2. Yeah, so it's false. Okay, so the last one, here we have a technician who's fixing a large number of computers. And we know that he fixes 2 per hour. Now we have to look at the question in order to determine our mu, which is our rate, right? So the problem states that at least 4 computers are being fixed in the next 2 hours, and we have to calculate the probability for that. And because we see that we're talking about the next 2 hours, this is our new time interval, and based on these 2 hours, we have to define our mu. So what is our mu in this case? What is the rate if we're looking at 2 hours as our interval? Think of it, he's fixing 2 per hour. If we're looking at 2 hours now, how many is going to fix in 2 hours? Well, 4, right? 2 times 2. Okay, so this is our mu. It's always the most important step. Get your mu, and then yeah, just use the formula or look it up in the table. In this situation, we're looking for x being larger than or equal to 4. So we need to use the complement rule because the table only shows us values for smaller than or equal to. Yeah, so we take 1 minus the probability of x being smaller than or equal to 3. And yeah, just look it up in the table, plug it in, and get a value of around 56%, which is bigger than 50%, so it's true. Okay, any questions regarding the discrete probability distributions? Anything? No?